This is Purbita Chatterjee from UTA Physics Department, and today I'm going to present my work on traveling ionospheric disturbances detection using deep learning models. So the Earth's ionosphere being a charged region of the upper atmosphere, it has a lot of complex processes going on, and it can be coupled with both the lower atmospheric region, basically the tropospheric region, as well as the upper atmospheric region, basically from the high latitude ionospheric region. So when it gets forced from the lower atmospheric side, that is basically from the tropospheric side, the climatological events like the hurricanes, tornadoes, and convective storms, they are mostly responsible for that. So because of this hurricanes and tornadoes, the atmospheric gravity waves gets generated, and they are capable of transferring the energy and momentum from the lower atmospheric region to the higher atmospheric or the ionospheric regions. When these AGWs in turn reach the ionospheric heights, they can perturb the local electron density there via ion-neutron collisions, and this generates some perturbations which are referred to as the traveling ionospheric disturbances or TIDs. Now, these TIDs are very severe source for severe scintillations in the GNSS and satellite navigation signals, and they needs to be properly detected. In this study, we are performing one statistical analysis to observe the concentric TIDs induced by the climatological events like a convective storm as well as a tornado. And in next, I would like to walk you through a model that we developed in detecting the TID regions over the contiguous events. So first, I would like to walk you through the data set that I've been using here. I've been using the GNSS data set that this data has been collected from the dense GPS receivers that are sparse over the whole of contiguous EOS region. That the TEC values that has been the total electron content values that has been created that has been collected from this GPS receivers have been detrended to observe the small scale variations of these TIDs, and that has been what I have plotted here. So what you can see, even though it's a little difficult to see here, you can see that these are the DTC amplitudes plotted against the longitude and the latitude of the North American region map, and you can see that these are the perturbations of the DTC. So if we can put our eyes over this circular region, you can see the perturbations are mostly circular. These are the TIDs that are generated. The star region here in both of these places represents the center of the deep convection storm. Now, if we fix this latitude value of this deep convection storm and plot the DTC values with longitude as well as time, what we get is the propagation characteristics of this TIDs. So for this one, this convective storm even of 4th April 2014, the eastward, west, and westward direction of the TIDs is what I have shown here. So as you can see, these waves are very much asymmetric, and that's very true because it can happen for this kinds of concentric TIDs. This is for another event. I have exactly done the same thing that I did here, and as you can see here, also here, the time period and the frequencies are not the same. Next, we move on to developing a deep learning model that can efficiently detect these TID regions over the TID maps of North American region. So for that, we are using a training data set of April 4th and October 7th. It's a hurricane event, and validation data sets for 2 different hurricane events, and a test data set for an entirely different tornado event. And we are using a YOLO model at the background. So this is what our training and the validation data set maps I have generated with some resolution values, and this is what the model is currently detecting, the TID regions. So here you can see the model, it's the TIDs observed here, and it's detecting with 75 and 52% respectively. So in the next future work, we plan to develop a mask RCNN that can effectively extract these wavelengths of these TIDs and measure the time period frequency as we did here for statistical study. And next, we would like to extend our work for statistical analysis over a whole solar cycle to observe the seasonal as well as the solar cycle dependence of these TIDs. Thank you.